Lighthouse Scientific Education presents a lecture in the Acid and Base series. The topic, Acids and Bases, Basics. Material in this lecture relies on an understanding of the previous lectures, water, aqueous solution, naming compounds, net ionic equations, and ionic bonding. While the terms acid and base are not new ones, a fuller description of what they cover is warranted. A review of the naming structure of acids and bases, as covered in the naming compounds lecture, is presented. Then it is on to the different definitions of acids and bases. The three described in this lecture are Arrhenius, Bronsted-Lowry, and Lewis. The first two will be given extended coverage. The Arrhenius definition is probably the most important at this level of study. This is the acid and base that we've seen in the neutralization reaction. Since the acids and bases are ionic compounds, they fall under the heading of electrolytes. The description of strong and weak electrolytes is extended to strong and weak acids and bases. Finishing the Arrhenius section is an introduction to polyprotic acids. The second major definition of acids and bases is that of Bronsted-Lowry. Within that definition, the important concept of conjugate acid-base is explored, along with a brief look at amphoteric compounds. Finally, we will look at a particular reaction of acids with metals. Before delving deeper into details, let's get an overview of acid and base properties, comparing acids with bases. Acids tend to taste sour, like with citrus fruit, while bases are often bitter or chalky tasting. That bitter taste with cucumbers is from a base. Acids can corrode metals. Rust is accelerated by acids. Bases feel soapy or slippery. A bar of soap is basic. Acids have a pH lower than 7. pH is a topic of the next lecture. Bases have a pH higher than 7. Acids turn blue litmus paper red. Litmus paper is a topic also covered in the next lecture. Bases turn red litmus paper blue. Many acids, but not all, react with bases to form salts and water. Many bases, but not all, react with acids to form salts and water. From these last two, we see that there's a complementary relationship between acids and bases. As for usages, commonly found acids include vitamin C. It is called ascorbic acid. Carbonic acid gives fizz or zest to soft drinks or sodas. Hydrochloric acid is the stomach acid used in digestion. Sulfuric acid is battery acid. Usages for bases include the soaps we clean with. Oven cleaner are often powerful bases, as are the chemicals used to unclog drains, like Drano. Milder bases make good household cleaners, like 409 and Windex. Some common acids we might have come across in our studies include nitric acid, hypochlorous acid, sulfuric acid, phosphoric acid, carbonic acid, acetic acid, and oxalic acid. Common bases include sodium hydroxide, ammonium hydroxide, calcium hydroxide, magnesium hydroxide, iron 2 hydroxide, calcium carbonate, and ammonia. Sometimes naming of acids and bases is included with the general study of acid and bases, and sometimes it is included in the section devoted to naming molecules and compounds. For us, it is discussed in detail in the Naming Compounds lecture in the Molecules and Compounds series. A brief overview is offered for those students wanting a refresher. If this is your first pass through the material, it is probably better to view the more complete description in that earlier lecture. First, to bases, and this is limited to bases with hydroxyl groups. For these ionic compounds, use the rules for naming ionic compounds. For acids, there are two naming structures. One is for binary compounds, that is a metal, hydrogen, and a nonmetal like chlorine, bromine, or sulfur. The second is when the acid has a polyatomic anion. That includes the important group oxyacids. Let's do bases first. As said, naming bases is the same as naming ionic compounds, limiting the naming structure to just bases composed of cations from columns 1 and 2 on the periodic table. We have a two-step process. Step 1 is to write out the metal element's name. Step 2 is to write out the polyatomic anion name, like hydroxide. Pretty straightforward. NaOH will serve as an example. It is an ionic compound with a metal cation and a polyatomic anion. Rule 1 says to use the metal element's name, sodium. Rule 2 says to use the name of the polyatomic anion, hydroxide. The base is sodium hydroxide. A second example is CaOH2. It is an ionic compound. Rule 1 says to use the element's name, calcium. Rule 2 says to use the name of the anion, hydroxide. Calcium hydroxide. Notice that there is no place in the name for the 2 subscript of the hydroxide. Proportions are not included in the name. Rather, they are deduced from the charge on the ions. The first of the two acid naming structures is for binary compounds. That is when there are only 2 types of elements in the name, and one of them will be hydrogen. Step 1 starts the name with the prefix hydro for hydrogen. In step 2, we write out the stem of the element name of the second element, that is the non-hydrogen element. What is meant by stem will be covered shortly. To that, add IC. Finally, add the term acid to the end of the name. For example, what is the name of HCl? Step 1 has us begin the name with the prefix for the hydrogen. The name begins with hydro. To that, add the stem of the element chlorine. The stem is generally found by taking the full name and dropping the last syllable. The stem for chlorine is chlor. To that, add ic. Cap it off with the word acid. HCl is hydrochloric acid. The more complicated naming structure is for acids with polyatomic anions, and in particular, those carrying oxygen, oxyacids. They begin with a polyatomic anion name. Take the root or stem of the name. This usually means dropping the ITE or ATE at the end of the name. Some polyatomic anions have a prefix before the name, like hypo or pre. Keep that. The more complicated part of the naming is what to add to the root. There are 2 options, and they are based on whether ITE or ATE was dropped from the polyatomic anion name. Add US, OUS, for ite containing anions, or add IC, for ate containing anions. Finally, add the term acid to cap off the name. Consider the common acid HNO3. To properly name it, start by getting the name of the polyatomic anion and clip off its end. Perhaps the name nitrate has been used enough in your studies for you to have memorized it. Perhaps not. There are always lists of polyatomic anions around, and they can be searched when a less familiar anion is used. Nitrate has a root, or stem of NITR, and a suffix of ate. Keep that ate in mind, as it is removed from the name. A decision has to be made to the ending. Since nitrate has an ate ending, add ic to the NITR, nitric. Adding the word acid completes the name, nitric acid. If more clarity is sought in naming acids and bases, return to the earlier naming compound lecture. Now it is on to definitions of acids and bases. There are three common acid-base definitions in general chemistry. We will outline three and then focus on the first two. Arrhenius acids and bases are found in aqueous solutions. They take place in water. An Arrhenius acid increases the hydrogen ion concentration in a solution. An Arrhenius base increases the hydroxide concentration in a solution. As an example, aqueous hydrochloric acid plus aqueous sodium hydroxide, producing the salt aqueous sodium chloride, and water. A Bronsted-Lowry acid and base takes place in any solvent, including water. That means an Arrhenius acid or base can also be a Bronsted-Lowry acid or base. A Bronsted-Lowry acid donates protons, hydrogen ions, in a reaction. A Bronsted-Lowry base accepts protons in a reaction. An example of Bronsted-Lowry acid-base reaction is water plus ammonia, producing ammonium ion and hydroxide ion. More on how this reaction matches the definition later in the lecture. The last definition is the more inclusive Lewis acid and base. It is a more advanced understanding of acids and bases, and usually involves the making and breaking of covalent bonds. It is an important topic in more advanced chemistry courses like organic chemistry. Briefly, Lewis acids accept electron pairs. Lewis bases donate electron pairs. The general form of this looks like this. The base shares 2 electrons with the acid, forming a covalent bond. Lewis acid-base chemistry is found in the study of electrochemistry and in the redox reaction. That is all we're going to cover with Lewis acids and bases in this lecture. Now we will focus on the first 2 definitions, starting with Arrhenius acids and bases. As mentioned, they take place in water, and the acid increases the hydrogen ion concentration in the solution. Taking a step back, let's relook at what a hydrogen ion is in water. Starting with the element hydrogen, it has 1 proton and 1 electron. If the electron were somehow removed, all that would remain would be a single proton. A hydrogen ion is a proton. However, hydrogen ions, protons, do not exist alone in water. They react with the water molecule to produce hydronium ions, H3O+. In water, a hydrogen ion is a proton and is a hydronium ion. In water, they all represent the same thing, and for the most part are interchangeable. Hydronium ion, though, is the more accurate description. The most defining feature of Arrhenius acid and bases is the neutralization reaction. The acid and base reactants are usually ionic compounds, and solubility can come into play. In water, an acid, the hydrogen cation, and a base, the hydroxide anion, react to form a salt and water. Water is considered neutral, and the basis for the name neutralization. A further look at neutrality is given momentarily, and a deeper look is found in the pH and titration lecture. As for a salt, this neutralization reaction is the definition of a salt, though it can be expanded to include most neutral ionic compounds. While we're doing definitions, here's a term that you've probably heard before: alkaline. It is the ability of a substance to neutralize an acid. It is often used interchangeably with basic, but it really should be limited to bases with cations from column 1 or 2 of the periodic table. Sodium, magnesium, calcium, those guys. We first came across the neutralization reaction in the Types of Chemical Reactions lecture. It is a form of the double displacement or double replacement reaction. The cation of one reactant ends up in a new compound with the anion from a different reactant. The opposite argument can be made with the salt. Neutrality can be shown more specifically by getting the net ionic equation of this common acid-base reaction. 2 lectures have already been given over to net ionic equations, so we will treat the process as being somewhat familiar. It begins with a balanced chemical equation. This one has no displayed coefficients, but it is balanced. The next step is to check and see what compounds in the reaction are soluble in water. Turns out that the acid, the base, and the salt are all completely soluble. Take that understanding to the next step. Write out a total ionic equation. That is, for each soluble compound, write that compound out as ions, like aqueous hydrogen ion and aqueous chloride ion from the HCl, and aqueous sodium ion and aqueous hydroxide ion from the NaOH. Same goes for the salt. The water, however, is left as a molecule because while it can ionize, it does so infrequently, and it is more accurate to leave it as a molecule. Water's ionization is discussed in the next lecture. Now, cross out spectator ions. These are ions that are the same on both sides of the equation. The chlorides are unchanged and are therefore spectators. Same goes with the sodiums. The last step is to write out the net ionic equation. Do not include spectator ions. Our neutralization reaction reduces down to the hydrogen ion plus the hydroxide ion, forming water. This is the heart of an Arrhenius acid-base reaction and follows straight from the definition. Let's keep the total ionic equation and consider Arrhenius acid and bases from the perspective of an electrolyte. That is a liquid that conducts electricity. It does so because it contains ions. Using solution terminology, if a solute completely dissociates into ions, it is a strong electrolyte. The hydrochloric acid, sodium hydroxide, and sodium chloride all dissociate into ions. They all form strong electrolytes. If, however, a solute partially dissociates into ions, it is a weak electrolyte. Given these definitions of strong and weak electrolytes, it is a small extension to argue that if the solute is an acid or base that completely dissociates into ions, it is a strong acid or base. A strong acid and base is a strong electrolyte. The term strong can be misleading. A strong acid does not mean it has to be corrosive or really dangerous. It also doesn't mean that the acid or base is really concentrated. It just means that the acid or base dissociates completely in water. Strong implies a capacity to carry electricity, and nothing more. It also follows that acids or bases that only partially dissociate into ions are weak acids or bases. Weak acids and bases are weak electrolytes. Weak does not mean that an acid still cannot burn, be corrosive, or be very concentrated. Weak is the limited ability to carry electricity in an aqueous solution. Very few of the many kinds of acids and bases are considered strong. Since the list is small, the names of strong acids and bases are generally memorized. For acids, there is hydrochloric acid, hydrobromic acid, hydroiodic, perchloric acid, sulfuric acid, and nitric acid. One way to help memorize some of these is to note that 3 of them have anions in the same column on the periodic table. Other than fluoride, the top halides of the column all form strong acids. As for strong bases, these are compounds of hydroxide with group 1 metal cations. Consulting the periodic table, we have lithium hydroxide, sodium hydroxide, potassium hydroxide. And then there are the hydroxides of group 2 metal cations, excluding beryllium and magnesium. That leaves this part of the column and produces bases such as calcium hydroxide, strontium hydroxide, and barium hydroxide. These +2 cations form bases with 2 hydroxide anions. That's it for strong Arrhenius acid and bases. The final topic with this definition is polyprotic acids. Some acids are capable of losing more than 1 proton per compound in an acid-base reaction. These are polyprotic acids. Poly means more than 1. Consider this table with column headings indicating the number of protons an acid can deliver in solution. Mono means 1. Hydrobromic acid can only release a single proton, as can nitric acid, and acetic acid, a weak acid. Weak and strong are not determining factors here. The next column are the diprotic acids, which include sulfuric acid. It can donate both of those hydrogens, but that second hydrogen does not come off easily. There is carbonic acid. It too can donate 2 protons. Phosphoric acid is triprotic. It can donate all 3 protons, but the second and third hydrogen do not come off as easily as the first. To further demonstrate the point, a closer look at sulfuric acid is offered. Being a strong acid, it readily loses a proton. Without that proton, it becomes HSO4-1, which itself is a weak acid. It still has an acidic proton. Under certain conditions, it releases that to solution. The remaining sulfate ion has no more hydrogens. 2 protons are released, diprotic. Titrations with polyprotic acids is covered in the pH and titration lecture. The second important definition of acids and bases is the Bronsted-Lowry. It is broader than the Arrhenius definition because it is not limited to just aqueous solutions, like it is in the Arrhenius definition. A comparison of the definitions shows that for acids, they're really quite similar. Both are giving up a proton. Where they really differ is in the definition of the base. The Bronsted-Lowry base is a compound that accepts a proton, where Arrhenius bases produce hydroxide. Yes, hydroxide ions readily accept a proton, but Bronsted-Lowry bases include anything that accepts a proton, and that is just a broader group of compounds and ions. The difference can be demonstrated with a series of Bronsted-Lowry acid-base reactions. In this first reaction, nitric acid is a Bronsted-Lowry acid. It is also an Arrhenius acid since the reaction takes place in water. It donates or loses its lone hydrogen. Water is a Bronsted-Lowry base. It gains a proton. No hydroxides are produced in this reaction. In the next reaction, water is the acid. Why? Because it donates or loses a hydrogen. That is the definition of a Bronsted-Lowry acid. The base is the sodium fluoride. Really, it is just the fluoride ion. Bronsted-Lowry acids and bases can be ions. It's sometimes necessary to consider the dissociated form of the salt when looking for Bronsted-Lowry acids or bases. With the ionic form of NaF, it can be seen that the fluoride is a base because it gains or accepts a proton. That is the definition of a Bronsted-Lowry base. Yes, Bronsted-Lowry acids and bases can be hard to identify. The simplest way to approach a Bronsted-Lowry acid and base reaction is to first ask which compound loses an H, a proton. That will be the Bronsted-Lowry acid. Then ask which compound gains an H, a proton. That will be the Bronsted-Lowry base. Keep these hints in mind as we tackle the next equation. Which compound loses an H? The HCl loses an H. Hydrochloric acid is a Bronsted-Lowry acid. Which compound gains an H? Ammonia gains an H. It is a Bronsted-Lowry base. One more. Which compound loses an H? The hydrogen cyanide loses an H. Hydrogen cyanide is the Bronsted-Lowry acid. Which compound gains an H? Same as the previous example, ammonia gains an H. Ammonia is a Bronsted-Lowry base. This gain or loss of a single proton can be taken one step further. Reaction between acids and bases produces conjugate bases and acids. The term conjugate in this context is defined as joined together in a pair. The pair is an acid and a base, or a base and an acid. These pairings can be shown with a generic reaction that has a Bronsted-Lowry acid, HA, reacting with a Bronsted-Lowry base, B. Conjugates are always on the other side of the reaction. They are traditionally products as written in the chemical equation. The acid HA has a conjugate pair. It must be a base. An acid and its conjugate base differ by a single proton, hydrogen ion. This pair differs by a single hydrogen. A-1 is the conjugate base to the acid HA. The base also has a conjugate. It must be an acid, and the two differ by a single proton, hydrogen ion. This pair differs by a single hydrogen. BH plus is the conjugate acid to base B. The basis of the conjugate pairing is the reaction direction arrows. This double arrow says that the reaction is simultaneously going in both directions. Reactants are forming products, and products are forming reactants. That hydrogen ion is transferring back and forth. The Bronsted-Lowry acid is losing the hydrogen ion and becoming its conjugate base. But the conjugate base can grab back a hydrogen ion and reform the acid. Where does it get the hydrogen ion? The Bronsted-Lowry base had originally gained the hydrogen ion, and it became a conjugate acid. As an acid, BH plus can donate back the hydrogen ion to the conjugate base A- in an acid-base reaction that reforms the reactants. The hydrogen ion is bouncing back and forth. A compound has an acid form and a base form, depending on whether the hydrogen is bound or unbound. There is, however, a level to which the transfer of the hydrogen ion occurs. Strong acids have weak conjugate bases. A strong acid completely or nearly completely gives up its hydrogen. It does not take it back easily. That means the conjugate base is not a good base. Weak acids have a strong conjugate base. Weak acids only infrequently give up their hydrogen ion, and they easily take them back when they do. The conjugate base must therefore be strong. Strong bases have weak conjugate acids, and weak bases have a strong conjugate acid. Same type of argument works with the base as it did with the acid. In the pair, if one is strong, the other is weak. Using the generic acid-base reaction as a template, we can diagram real-world reactions for conjugates. Here is nitric acid being added to water. Water is the base in the reaction with a strong acid. To get an acid with its conjugate base, find a pair of compounds that differ by a single hydrogen. The acid is on the reactant side, and the conjugate base is on the product side. To get a base and conjugate acid, find a pair of compounds that differ by a single hydrogen. The base is on the reactant side, and the conjugate acid is on the product side. Starting with nitric acid. Losing a hydrogen ion leaves the polyatomic ion nitrate. It is the conjugate base. Nitric acid is a strong acid, so nitrate must be a weak base. For the base, water. It picks up the hydrogen ion and forms hydronium. Hydronium is a conjugate acid. It is a strong acid, and water is a weak base. Here's another. Water acts as the acid, and the sodium fluoride is the base. How do we know that? How can we tell if water is a Bronsted-Lowry acid or base? The answer is to look for the pair that differs by a hydrogen. Water loses a hydrogen ion and forms hydroxide. Water is a weak acid, and hydroxide a stronger base. Harder to see is the fluoride. It switches out the sodium for the hydrogen ion. As a net ionic equation, the sodium ions are removed, the pair becomes more obvious. Hydrofluoric acid is a weak acid, so the fluoride ion must be a stronger base. Keep an eye out for that aqueous subscript. If the reaction takes place in water, the compounds of interest might just be ions. In this last example, we will find the pairs first and then assign acid-base designations. Ammonia and ammonium differ by a hydrogen, as do hydrogen cyanide and cyanide ion. Since ammonia is gaining a hydrogen, it is a base. Ammonium is the conjugate acid. Since the hydrogen cyanide is losing a hydrogen, it is the acid, and the cyanide ion is the conjugate base. This designation process takes some practice, but it soon becomes a skill. The last topic with this acid-base definition is amphoteric, and it is connected to polyprotic acids. Amphoteric, a compound including molecules and ions that can react as an acid as well as a base. Importantly, it can be used as a buffer, which is a topic in the pH and titration lecture. Say we have the diprotic acid, carbonic acid. It is a weak acid, but sometimes it gives up a proton, leaving the compound bicarbonate, HCO3-1. Sodium bicarbonate is baking soda. Bicarbonate is amphoteric. It can act like an acid and release a proton, leaving the carbonate ion. Bicarbonate can also act like a base. It can accept a proton and reform carbonic acid, H2CO3. Bicarbonate can give up a proton like an acid or pick up a proton like a base. That completes the Bronsted-Lowry review. The last topic of the lecture is the reaction of an acid with a metal, and we will limit the discussion to a specific type of reaction. Some metals react with acids to form hydrogen gas. For example, adding sulfuric acid and zinc together forms the salt zinc sulfate and the gas hydrogen. These reactions are commonly incorporated in the labs of a general chemistry course. The volume of hydrogen gas is captured and measured and then used in stoichiometric calculations to determine the percent yield of the reaction. Sometimes different acids or metals are used, but not all metals react to the same degree. Metals can be listed in order of how reactive or active they are with acid. The metal hydrogen is in the middle of this list, and any metal that is more reactive than hydrogen is listed above, and metals that are less reactive than hydrogen are listed below. Sodium is one of the most reactive metals. Listed in decreasing activity are magnesium, zinc, iron, and lead. Any of these metals would be able to produce hydrogen gas in this common lab experiment. Lead would probably take a while. Metals that are not good candidates to produce hydrogen gas include copper, silver, and gold. These metals make better jewelry because they are less likely to react with the acid in our sweat and form hydrogen. Usually a table like this is provided to the student since the reactivity cannot be predicted at this level of chemistry. And that concludes the material of the lecture. As a recap, acids generally have a sour taste, corrode metals, and have a pH lower than 7. They turn blue litmus paper red and react with bases to form salts and H2O. Bases have a bitter or chalky taste. They feel soapy or slippery. They have a pH higher than 7. Bases turn red litmus paper blue and react with acids to form salt and H2O. 3 definitions of acids and bases were offered, and deeper exploration of 2 of them were made, including Arrhenius acids and bases. These reactions can only take place in water or aqueous solutions. An Arrhenius acid increases the hydrogen ion concentration in a solution. In water, a hydrogen ion is the same thing as a proton, and actually found in the form of hydronium ion. In water, these 3 terms are pretty much interchangeable. An Arrhenius base increases the hydroxide concentration in solution. One way to remember the Arrhenius definition is with an acid-base neutralization reaction. When expressed as a net ionic equation, the acidic hydrogen ion and basic hydroxide ion combine to form water. Arrhenius acids and bases can be electrolytes. Like a strong electrolyte, a strong acid or base completely dissociates into ions. Strong only refers to the ability to dissociate. Strong is the capacity to carry electricity in water. Like a weak electrolyte, a weak acid or base partially dissociates into ions. Polyprotic acids can donate more than 1 proton. They have more than 1 acidic hydrogen. The second major definition of acid and bases is Bronsted-Lowry. It is a broader definition since the reaction can take place in any solvent. A Bronsted-Lowry acid donates a proton. A Bronsted-Lowry base accepts a proton. As the reaction proceeds, a Bronsted-Lowry acid becomes a conjugate base, and a Bronsted-Lowry base becomes a conjugate acid. A compound is amphoteric if it can react as an acid as well as a base. Bicarbonate is an example of such a compound. Some metals react with acids to form hydrogen gas. Reactivity of metals is found in a table. And that concludes our lecture. Acids are about protons.